So we want to do a couple of examples about how to classify differential equations. So I have a couple of examples up here, and we'll go through each one in turn and identify the important components in terms of its order and its linearity. And then we'll also talk in a couple of cases about whether or not the equation is homogeneous. Alright, so for the first example, we have our differential equation here. And so we want to identify first the order. The order is determined by the highest degree derivative in the equation. Now, in this case, this is a first order equation because the derivative is only happening one time. After they take the derivative, they are then cubing that equation. So it's important to note that dy dx cubed is not the same as d cubed y over dx cubed. So in the latter case, this is a third derivative. This is a first derivative which is being cubed. They are not the same. So in this case, the order is 1. But because this first derivative is being cubed, this is not linear. Yeah, this is enough. Anytime you take a derivative or a function of y and you do something to it, like multiply them together, raise it to a power, put it inside another function, that makes it not linear. We don't care what the x is doing. We only care what the y function is doing. Okay, so let's go down to our next example. Here's our second example. So again, the order is the highest degree of the derivative in the equation, and that highest degree is 2. So this is order 2 because it's a second degree. Is 2. Even though there's a first derivative in here, we care about the fact that this is a second derivative, and so the second derivative is what counts. Now, in terms of linearity, this second derivative is by itself. This function of y is not being multiplied by any other functions of y. This y prime is not being multiplied by any functions of y. So this is linear. Now, it turns out that this function is also homogeneous because if it's linear, this is already not homogeneous. It's not homogeneous because when it's linear like this, we want to look to see if there are any terms that contain only x and not y. And so therefore this is not homogeneous. Okay, so let's look at our third example. Our third example contains a higher derivative, and so I've actually written the equation twice just so that you can see what some of the different ways are to write this derivative. In fact, if we wanted to, we could write this one additional way. All three of these equations are exactly the same equation. So this is a fourth derivative, so sometimes you'll see it written in Roman numerals, and after you run out of 3 primes, then sometimes you'll see that. Sometimes you'll see it written as in parentheses, because y to the fourth, with just a 4 without the parentheses, is a power of y. But with the parentheses, it's meant to indicate that this is something different, and in this case, it's actually a derivative. And then the prime is there by itself, or you will see it in Leibniz notation like this. These are all the same equation, and these are all order 4, because the highest derivative is the 4th derivative. This is also linear, because each of the derivatives, the 4th derivative, the 1st derivative, they are not multiplied by another function of y. They're not inside another function of y. And then this is also non-homogeneous, because we have this extra term out here that contains only x. All right, so going down to our next example. This example we can immediately see is non-linear, because we have a derivative of y multiplied by another function of y. And it's actually nonlinear for another reason, because tan y also makes it not linear. So if either of these terms occurred in the equation itself, by itself, it would be nonlinear. The fact that they occur together doesn't really change that. We would also have to indicate that the order is 2, because the highest derivative in the equation is y double prime. And then finally, the last example, this is a first order equation because of order 1, because there's only a first derivative in the equation. And it's nonlinear because we have y cubed over here. We also have natural log of y is something. So there's several reasons why this would be considered nonlinear. In addition, first order equations have sometimes a slightly different definition for what constitutes a homogeneous equation. And so in order to test whether this equation is homogeneous or not, we actually have to do a test. And the test is replace x with tx and y with ty, and then see if the t factors out. So in this case, I'm just going to copy my equation. So we'd have tx and ty, and so tx cubed would be t cubed, and ty quantity cubed would also give me t cubed, and then this would give me t squared, and then this would give me another t. So look what happens. I'm going to be able to cancel these two t's, so I'm going to get ln y over x again. And then these t cubes are going to factor out, and I'm going to be left with my x cubed minus y cubed. And then in the denominator, I'm going to get t cubed, because I have t squared and another t, but then also x squared and y. And so now I can cancel out my t cubes, which is going to give me back my original equation. And so this is, in fact, homogeneous first order. If your equation is not in this format, first solve for y prime. And then, now if it's not solved for y prime, you can still do this test, but then you would have to factor the t all the way out of the equation, because it wouldn't be a ratio, and so it wouldn't cancel. So like if you have a dy dx equation, then factor out copies of t. and they would have to factor out completely. The factor of t that you end up canceling, in this case t cubed, or the factor that you end up factoring out of, you know, an m dx and dy equation, the order of the homogeneous equation, this is a different kind of order, is the power of t factored or canceled. So this would be a third order homogeneous equation. And this is one of those solving techniques that we're going to encounter later on, where this will be important. But this is how we identify order of the equation with the degree of the number, the power. The non-degree is another thing, but the order is the number of derivatives in the equation, the highest one, and then whether the equation is linear or nonlinear depends only on y. And then homogeneous for first order equations is special, and homogeneous for non-first order equations has to do with this, is there a loose power, a loose term that has no y's in it and only x's. If every term has a y in it, it's homogeneous, and if there's a term that has x's in it, then it's not homogeneous.